or we can continue in German, but I think most of the people will not be that happy. So I'm very happy that you guys are here. I'm very happy for the event this evening, and I'm very happy that Philip and his group, sitting behind and around you, agreed to demonstrate a little bit what they do with deep learning, artificial intelligence, and whatever. And so Philip is heading the group, and he will give a short introduction, and then they will do some music and show you the tools they have. And the goal is just to get with you guys into discussions and to see what you would be interested maybe. Yeah. So I think we just started. I think we don't have to introduce, we do it afterwards.
No, I think. Thank you so much, Marcus. So I don't think I have much to say left. So basically, he said everything. So my name is Philip Essling. I'm a professor at Sorbonne University, and I'm researcher here. And I head this little group called ACIDS. So ACIDS actually stands for something. It stands for Artificial Creative Intelligence and Data Science, just to be a little bit more serious. So our goal is actually to invent some AI methods just for human musical creativity. And I just want to give you a little bit of sense. I'm going to do a little tiny speck of mathematics, but really not so much, just so we understand everything together. So the idea of our group is actually first to understand music. And music is actually a temporal problem. It's also a combinatorial problem, because music is time and music is also mixture, right? So the problem is that it's a multimodal question. So first we need to understand audio signal so that we can actually interact with audio signals. So interacting means knowing how variations of audio actually behave. And this is a problem of the complexity of audio and a problem that we need to push towards what we call co-creativity. So once we know how to interact, we want to generate stuff. So generating means exploring inside audio signal, perceiving audio signals, and allowing what we call ideation, right? So we have a huge program today. So we took like everything we had and split it up around. So together today, we're going to go through first understanding musical space and machine learning. Then we're going to see how we generate audio signals, and we try to go from these self-sufficient machines, which everybody knows, you know, when you push a button and it just generates. And finally, we're going to see how we interact with these tools. So basically, what we call control learning, and we have real-time and embedded instruments, for instance, EuroRack, that you will see, because then we have two presentations. So first, the amazing Antoine Caillon is going to show you how we do real-time creation with our tools, and then the splendid Ninon Devy is going to introduce the NeuroRack, which is the first deep learning EuroRack synthesizer that is just there. So first, let me start with a completely dumb question. So what is music? I hate this slide. But yeah, I just want to convince you that music is simply a question of space. So why am I saying that? Because I think music lives in different spaces. So everybody knows about the space of the waveform. So this is where acoustics belongs. So music is a series of points from hair that vibrates. So then we can try to understand better by looking at spectrum. Spectrum means frequency across time. So basically this is where signal processing lives, a series of frequencies that evolves. And finally you have symbolic scores. So everybody knows this, and this is where computer music belongs. So music is seen as a set of discrete symbols across time. So basically, if you take this direction, it's for understanding stuff. But when you want to generate, you actually have to go the other way around. So basically, our goal is also to see how we can transform this space to provide high-level interaction. Because we would like to interact with this level, but actually understanding something more than the last level, which is kind of, you know, old now. So basically, when I'm saying space, I'm actually really meaning space. If we take a waveform and we just split it in little chunks and we look at it, you can see, for instance, in triangle waveform, if we take 3 points, they have values, right? So actually having 3 values means that I can create a 3-dimensional space just to imagine what's going on. So basically this one would go at this opposite end of the space. If I just take another one and shift a little bit the point, it means I'm moving a little bit upwards in my space. But now the problem with this type of space and its complexity is that if I take the same triangle shape, but just phase it a little bit, it's going to go at the opposite end of the space. So this means that this space is not well behaved, because information is folded across space because of its dimensionality. So I'm going to introduce a theory, which is called the manifold theory, which states that inside a very complex space, there is actually a very simple information manifold, which is wrapped inside this complex space. And I love to do a little bit of a physical example before going further. So I have a sheet of paper. I love the sheet of paper. So basically, how many dimensions do you think this thing has? So you can say 2, right? Because we can't really go this way. Now, if I just do this, how many dimensions does it have? You think 3, but it's actually the same object, which means that basically it's a simple object of 2 dimensions, but it's folded inside a 3-dimensional space. So our goal is actually to try to unfold these objects, seen as complex, in a complex space, but to render them simple, right? So basically our whole goal is to transform this complex manifold into a simple object. So now that I showed you this, we can actually visualize it. So this entanglement, maybe it looks like this. This is actually from string theory. This is a real thing. But anyways, let's think, as I said with the waveform, if I have the number 4 represented there, on the manifold, on the complex structure, there is a simple path to go to a rotated version. And if you follow the same path again and again, then you're just going to rotate your object. And maybe something that lives very close, but it's actually very far in terms of path inside the manifold, is going to be a completely different object, even though they share a lot of similarity, right? So our goal is actually to transform this into this type of simple spaces. So if we can unfold this structure, then we can have simple linear path into high-level variation factors. So this is where I do a little bit of a live demonstration. So this is actually the first of our objects. So this is on the analysis side right now. So yes, so think about when you're going to make music on your computer and you open a folder, and this is just a sample folder. So this is also a space. If I just represent it, it's going to be like this. So actually you can visualize, now this is actually my space of audio, right? So if I'm moving across folders, so you can see my hand is going around, I'm going to try to find the sound I want, and it's going to take me forever, right? Because things are just organized by their name. So I'm just listening to bullshit all the time just to find the sound I want. First thing I can do is think, oh, I can be more clever, and maybe I can organize them by, here it's, sorry, this one is actually loudness and pitch. So this means I'm going to have like, not very loud stuff, I'm going to have louder stuff there. But you see, it's still kind of a mess, right? So now, with our first model, this is something we developed which analyzed the sound. It's going to make these type of structures. So we actually take exactly the same audio samples, we try to learn their relationships, and then to unfold the structure, right? And basically, if I go, I don't know, around there, it's only little... Sorry, my demo is a little bit messy. So basically, every part of the space is organized based on what it sounds like. Even though it's a complex structure, going across it, I can have, you know, here I have interaction that are not loud. I don't have audio anymore, maybe? Maybe not. Do I have audio? It's high pitch and long synth. If I go around there, it's going to be interaction sound, because pitches, this type of stuff. So you see, this is purely organizational. I mean, understanding how sound behaves and give you a simple space where you can just go around and say, oh, okay, I want something like, I don't know, maybe harsh. I don't need as much time and I don't need their names. I can just go around by perceptual similarity, right? So, first demo was a success. So I can go back and start to do, as I promised, a little tiny speck of math. So the little tiny speck of math is trying to understand how we can get to there and then go even further, right? So what we use is actually machine learning. So this is kind of the buzzword of the moment, but I like to simplify it like this. Nature kind of relates things together. So you take two objects and they have some relationships. So you have an input, X, and an output, Y. And the problem is that it's very complicated to understand how these two things belong together. So the goal of machine learning is actually to try to approximate nature, to find the relationship based on a function that we can tweak. So basically we have a model of the world. This model is this complicated function with lots of knobs. And basically we want to turn the knobs around until we can find the same relationship. So this means, for instance, if you have these sets of points, you want to understand how they relate. This is the real way they relate together, but we don't know this function. So basically we're going to have to make a model, and sometimes the model is too simple, sometimes it's too complex, but we can find actually the good relationship by tweaking the parameters. So now you've heard a lot about AI and neural networks. So AI and neural networks are actually very simple as well. Basically, if you look at one neuron is something which takes information in. So basically you have input signals, and these input signals are there summed inside the cell body. So it means you just take the sum of the inputs, and then you look if there is enough energy in the cell body, then the neuron fires. So basically, in terms of math, it looks like this. So it's y equals sum of wx plus t. But if we simplify it and just say, okay, I'm going to have only two inputs, then I can have this formula. And this is something we all seen in, high school, which is basically the equation of a line. So what the neuron does is actually it divides the space. So it tells you if something is above the line or under the line. And of course, moving this line makes you have different relationships between objects. And this more complicated formula is actually the generalization, which means it's an hyperplane in n dimensions, right? So why I'm saying this? Because I told you I want to find a way to transform space. But actually, if I look at the same equation in different way, I'm saying maybe I had some complex relationship and I just said a neuron is actually a line. So how can I have something which behaves more, like a real transform? Actually, if we generalize our previous equation and we look at it in 2 dimensions, we had something called the nonlinearity, which means actually now the space is going to be stretched and folded. So basically now we have everything we need because we can find a way to take these type of functions and actually stretch space around. So you can see neural networks as ways of stretching, folding the space in different ways. So this idea actually extends to very complex space. So if you take a space like I showed you with all your samples, we can also find a function, a way more complicated function, which kind of stretches the space around. So our goal is to find this mathematical unfolding so that we can have new ways of interacting with music in a more simple and direct manner, right? So this actually extends to musical creativity. So why am I saying this? Because you remember this complicated stuff. If I can unfold it into something simple, then I can have directions in which it makes sense, which means I can generate from this space more easily. And this is actually what we're going to see next. So first, I want to talk a little bit about the creative issues we have. So from what I said, you would say the problem is that this is a function. So a function means we are trying to solve one problem. And one problem would mean we evaluate the quality and we are actually doing something called convergent thinking. Convergent thinking would mean we have a problem and we have a solution, meaning that one problem equates to one solution, which is really not creative, right? Because if I have to select every time one problem and one solution, we cannot really generate stuff. So actually creativity is more about divergent thinking, which means we may think about problems or ideas and we want to have lots of solutions to this same problem. So actually we are using something called probabilistic machine learning. So the idea is we try to turn from data as points, as I told you, like one point is actually a full sound, to full distributions, which means that there is lots of information around that resembles. So this allows us to introduce something called latent variables, which are actually hidden variations inside the data. So basically, This means we can generate something by saying, I have this distribution that goes to a more complex distribution. And this is actually results from recent machine learning algorithms where you can just input, for instance, happy, and you will have happy faces. And so basically, this is also our goal with creative music machine learning. The final issue I want to talk about is actually, I'm going to move this one around. Yeah, I'm going to just talk a little bit about this one. I love it. Sorry. Historically, you know, the way we interacted with instruments and how they were devised is that we had these physical constraints and we would carve out physics to get the audio we wanted. So basically, we had the physical world, and creating the interaction led to the audio. And I think one of the biggest problems we have today is that this paradigm seems to be a little bit reversed, right? We can generate endless audio possibilities with computers and synthesizers, and now we have physical constraints on how we can interact with this. Because, for instance, a modular synth, you have so many knobs, you need to just go around and patch stuff. So basically, can we do the opposite, which is carving into the audio generation to fit some physical gesture? And we're going to see that in the end. And this is my last boring slide, I promise you, but I think it's interesting, like everything. Yeah, I'm interested by too many stuff. So there is still one profound thing, I think, and it's in the common imaginary of how artificial intelligence is used and how it creates music. Because most people think the AI does everything and it's just now the AI is the artist. But it depends on what you grant the AI in the creative process. Because you have, of course, the possibility to do these self-sufficient generators. You know, you just have this big create button and you push the create button and it creates. So, okay, that's completely useless, right? So the thing is, in the way to do better, you can have these interpolators, style transfer, you know, control without understanding, where you move around and it's doing something, but you don't really think you are the creator of this. So this is the black box paradox. And what we're trying to go towards, and hopefully we're going to show you, is fully co-creative tools, which are things that enhance your own creativity. And you can have the computer as a propensity to expand your own limit. If you have some time, I would recommend one paper we recently did with Nino, which is called Creativity at the Era of Artificial Intelligence. It's purely philosophical, so no math, no words. So basically now, it's only demo. So I'm going to start by showing you all projects we did in the team, which is based on this aspect of generative AI, because we had to start somewhere, and how today we are going to move towards creative AI, right? So first, generative AI. So this is, all of this is going to be past and undergoing works of our team. The first is, of course, what I said was stupid, to do a self-sufficient system, but to see how good it can be. So music is highly organized. So the idea is that we can kind of predict, if we take one slice of the waveform, we can predict the next one and predict the next one. So basically we build a system which allows to do this, which kind of predicts the following part of the waveform, but we do it with a very organized hierarchical nature. So basically, if I simplify this whole shit, is actually you have a generator and you have a push button that generates a waveform, and then it can kind of feed itself and generate indefinitely, right? And so this is a piece that we did in collaboration with Daniel Egizi in 2015, which is called The Fabric of Monsters. And it's very interesting because it was a reboot of Frankenstein's opera. And the whole opera is actually the machine learning on stage. So basically you can hear the process of evolving from pure randomness to actually speaking. And I tried to compile some of our examples, because if you start training your model, the first day it's actually random. It doesn't know anything, so it's pure noise. After 1 day of training, it gets you this. You can hear some events coming. The third day, it learns something very important. It learns to shut up. After the fourth day, it's trying to speak again, so it's still a little bit messy. And if you keep training for 15 days, you're going to have this result. So, I don't know if you speak French, but I can tell you this is not French. I don't know if you speak any language in the world, this is not any language in the world, right? Because it just learns to generate these little chunks that looks like what we give. So the idea in the end is that, I love it, there is a part where it takes its breath. It was before, sorry. And then we trained on opera. So everything you hear is generated, purely. If you listen carefully, actually it's very interesting. Oh, sorry. It's very interesting because in the end, you have to listen to the violin, which follows exactly the voice without any attack, right? So basically you can hear, it's kind of following the same temporal pitch, and you have never an attack of the violin, which is physically impossible, but sounds okay. Okay, so very recently we extended this idea with Adrien Biton in a manner where we thought, okay, we have this thing that generates forever. The problem is how we can try to control this would mean we have a way to re-encode and control the thing, how it is pushed, right? Which would mean we could kind of put some waveforms and do stuff with it. But the coolest thing is that this actually gives us access to a control space. It's a very complicated space, but we can do what's called sampling, which means take a random point inside this space and ask what is going on in this point. And then we can move inside the space and listen to everything that is going on in the space. So actually, for the sake of this presentation, we trained a model specifically on the RASTER discography. So we use bars of 4 beats to try to capture some electronic aesthetics. And then we ask the model to generate, and it's supposedly trying to generate novel electronic styled bars. And so the idea is that we take this space and we take random points inside. And so it's very short, so it's going to be only 4 beats. This. Okay, so to have something which is a little bit nicer to hear, we can actually sample a point. So we take one point, and we take another point, and then we can generate everything in between, so it's going to be just a cut. Next point. Okay, so this is interesting, even though we don't really know what's going on. So now we have some form of control, but no form of understanding. So I want to show you what we are trying to do with creative models, which is actually more to try to understand. So I'm going to introduce one last model. It's the last promised. So the problem is that the previous methods do not provide an understanding. We just take points and go around space. So what we want is to further provide some things where we can understand, okay, I want to move the pitch around, I want to move the centroid, I want to have something with more beats, or this type of controls. So actually we reverse the paradigm, which means we first encode sound to understand it, and then we decode it from a probabilistic space. Which means in between now, we have this little space which explains a lot of things. So basically, this method is probabilistic and unsupervised, and we can automatically disentangle the major factors of audio variations, which provides an understandable, simple space. So it's a lot of keywords. It's just to say, in the middle, we're going to have something which explains what's going on with our examples, and then we can actually have some clear factors in every dimensions. So the first thing we did with the amazing Axel Schemler-Romer-Santos was to try to understand auditory perception. So basically using this, but trying to force this space to fit perceptual properties, like brightness and this type of descriptors. So what we did is we constrained the space and we mapped to a three-dimensional space, because we want also to have something where we can move around and understand what we are doing, not something with 100 dimensions, right? So we received an award for this work, just to say. So basically, it's very accurate in terms of how the properties are represented. It can actually predict perception on new instruments. And the coolest thing is that it organizes these properties very efficiently. So I think I have a video afterwards. So for instance, 1 point can generate this clarinet. So this is only from 3 values. So I'm just taking 1 point in my 3D space and say, generate what's there. And then the cool thing is that I can move around and, for instance, inject part of the piano inside a clarinet. So basically, you're going to hear at the beginning the hammer of the piano, but in the end, the windy aspect of the clarinet. So you have like kind of a mixture of both instruments. So yeah, this was the properties. So if you scan your space, you can see it's very linear in terms of brightness property. So we actually extend this idea to drums. The problem with drums is that they are mostly noisy. So we need to do this end-to-end training with waveform. So we just added this thing to inverse to noisy waveform. And basically, we add this, and then we obtain the same type of control space, but now for kicks, snares, claps, hats, and everything we gave the model. So the cool thing is that we just give a little bit of examples. We say, this is what I want to create. So I give kicks. And then it can generate everything that's going on between new kicks that sound not like my kicks, but in the same style. So this is actually something we did as an Ableton plugin, web-based interface. I'm going to show you the results first. So basically, I'm going to explain. I missed. Okay, sorry. So basically, this is the generation process. You have this space, and I'm just taking a random point. For instance, kicks are the red dots. So I'm just taking one random point around the kicks, and then I'm moving as a circle. And every time there is an event, I'm generating what's going on at this point where I'm at on the circle. So if you listen, I think the hats are the most compelling. Basically, you're going to see it shifts, it morphs the audio signal in a very smooth manner. So you can actually, this is clearer, I think, on the hats. Okay, and the Ableton Live plugin is actually a very simple thing. So basically, you can have 16 voices at the same time, and if you take one sound, you can move across space. So basically, you just select something, and you listen to what's going on. So you have brighter sounds up, shorter sounds right, or longer sounds right. Then when you select, you can play a melody with it. I mean, a sequence. You can do melodies with drums. Okay, so something is moving, and you can change your sound in real time. Okay, I'm gonna move because we have so many stuff to show still. So sorry, I'm going a little bit like a crazy person. So we also did some work on what's called style transfer, which means that AI can allow you to project some data on a new domain. So I'm going to explain myself. This is some form of analogical reasoning. Analogical reasoning means you connect some source, some properties that you want, but you want them with a style. So basically, you try to transfer the source content. So let's say I have this image of this beautiful person, and I'm trying to have it in this style. I think you all have seen this in terms of, image. It was everywhere in the papers. So the idea is to allow to keep the interaction method of the original space, but try to transfer the instrumental gesture. So this is what we did with something called differentiable digital signal processing. So we now take an even more direct approach, which is to take traditional signal processing. So you have source and noise, so sinusoids and noise. And basically here we make it differentiable, and the AI is not working on how to generate, it's working on how to control the generation. And this is the last part of my presentation where I show you that actually the future is to take some very nice way to synthesize and actually to learn high-level controls over these generation machines. So the results are quite cool. This is from the original paper from Jesse Engel. So basically, if you take a voice, I think it's Jesse, I'm not sure. Yeah, maybe. And basically you train with a violin. So you just have to sing, and we're going to show you afterwards a demo where you can just make noise, sing, and it will do like great sounds, but I can't say what it is yet. Okay, stop. Now you're starting to make me feel bad. So note that we have a set of descriptors in the middle, so we can actually say, I want brightness, I want loudness, I want this, I want that. And the model will train knowing that you want exactly these controls on your sound. So basically, ultimately, we could do any form of descriptor-based synthesis. So if you can annotate some sounds and say, this is punchiness, this is, I don't know, doriness or readiness. So basically, we take all these descriptors, brightness, flatness, anything, and we generate directly from it. This is how the interaction works in the end. So all of this is based only on a set of examples, and this is the great work we are doing with Ninon Deville and Jean-Baptiste Dupuis right there. So actually I have a live demonstration of this, but I think we are short of time. So maybe if you want, and we have some time, I can do it later because we still have too much to show. So actually this model was used recently with a composer called Alexander Schubert, and he did an amazing piece called Convergence, right? And it's, anyways, he was using exactly this model with Antoine Caillon here, and this is an extract of the piece. So basically, the sound you're going to listen to has been generated using our models in terms of generation, and we also worked with images, so the faces are generated in real time, and the sound is generated real time, right? So basically, you're going to see, yeah, you're going to see. The piece itself is around 1 hour and 10 minutes or something. So I'm not going to show everything. I have more extract if you're interested. But I want to show you my last little baby, and I would be perfectly on time. So audio synthesizers. I love audio synthesizer. I'm actually a synth nerd myself. So I hope everyone in this room is actually a synth nerd. So synths are everywhere. And the problem with synths is, there is no problem with synths, actually. There is no problem. The problem is that we are not good enough for synths. We were not born to have synths in our world. So maybe the problem is we are too limited to really understand everything in a synthesizer. The problem is more, how do we control and interact with synthesizers? So the problem first is that they increased in complexity completely. You know, we had this good old additive synthesizer, like Korg Electribe. It's like 2 buttons, yeah, nice. And now we have, you know, FM granular wavetable quadriband laser shotgun stuff. So the problem is that it's very painstaking to explore this type of, I mean, maybe people are better than me, but usually when I go, you know, and I listen to a sound, wow! I love this sound, you know, punchy, and I take my synth, and 4 hours later, I get this thing. So I think everyone in this room can relate. Thank you. So the other problem I found depressing with my synth is that the parameters have so much uneven impact on audio. Basically, if I take my synth, sometimes one parameter, I move it, I move it, I move it, I move it. What's going on? Nothing is happening. And then I move another parameter. So basically, how can I understand what is going on with my synth? Because there is no semantic or perceptual controls with synthesizers. So what we proposed is to see synthesizers as functions. They kind of relate together 2 spaces. One space of parameters goes to the space of audio. So implicitly, our two space are the parameter space and the audio space. If we take the parameter space, the problem I said is that if you take this, some parts are actually useful and some parts are useless in my space. You can think about if I have a dry-wet controller, it means if everything is dry, then all the parameters are useless, right? So some part of the space are ill-defined. And if we look at the audio space, some part can be done by my synth, but my synth maybe cannot do cats, for instance. So the process of synthesis is going from this space to this space. I want to find a way to go from the audio space back to the parameter space. The problem is that this is the space where we have control, and this is the space where we want control. So implicitly, what we are going to do is we're going to build an invertible mapping between these spaces. So this is what we called universal audio synthesizer control. So basically, instead of looking at things like this, which is basically audio is transformed and we try to perform inference to have parameters, which I think is useless, we propose this thing where first we use the same methods I showed you about compressing the space into something understandable. So we organize the audio space, then we organize the parameter space with the same type of ID, and then we build this mapping between the two stuff. So this looked like a little bit convoluted thing, but if we look at this, we can actually have lots of different nice things. Basically, first, it means that what I can do now is called automatic parameters inference, which means I can drop a wave file and have the parameters of the synth that sound the closest to the wave file I gave. Second thing is that this is organized, so basically it learns macro control based on audio. So if I move here, everything is going to move there, but it's going to make sense in terms of auditory perception. Finally, I can also do the inference, which means I can have parameter-based exploration. So what I mean is that if I like one preset, I can just go in the audio space and find other presets that I like with maybe completely different parameters. And finally, we wanted to have this semantic dimension discovery. We wanted to have something where we can just say darker, more aggressive. It doesn't work. But let's be honest, I tried for days. But I'm sure one day it will work. So I'm going to move maybe straight to the presentation. I want to show you some examples of reconstruction. So for instance, I'm using a very simple synth called Diva, which is a VST, which does additive synthesis. And if I give this from the MS-20, the reconstruction, so it infers the parameters, and with my other synth, it's going to give me this. So of course, the problem is that not everything can be done with every synth. I just want to show you, for instance, something where I think I laughed for maybe 10 minutes in my office, because I tried to reconstruct an eagle with an additive synth, and my model gave me this. This is I love this. Sorry. And so last thing is that, yeah, we can learn this kind of unsupervised macro controls. I think I'm talking too much, so I'm just going to show you. Live demonstration time. So now it's number 1, too many setups. Sorry, yeah. Oh, you're going to see my password. Okay, cool. So basically, this is what is called the flow synth. So the flow synth is an Ableton Live device. It's a Max for Live device, basically. So you need like the full license. Sorry, it's costly. So basically, what it's doing is that it's embedding a Diva synthesizer, I think is there. Yeah. So this is Diva, right? So if I listen to Diva itself, yeah, synth. So basically, this is very, basic. You can see that this is really Diva playing. So it's not very interesting. So now what I want to do is, for instance, I have my audio and I think, okay, I want this synth to sound a lot more like, it doesn't work. Why doesn't work? Why are you not working? No? Okay. Ah, haha, ha ha ha. Haha, so many errors. Okay, I want to have something more like this. So I'm just going to take my waveform. I want to show you how fast it is, because I'm proud. So basically, I'm just going to take my waveform, I'm going to drop it here, and bam, it changed all the parameters, and now it sounds like this. So of course, this is not the right pitch because I'm inputting MIDI, but if I go down, 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 I'm starting to have something which is really closer to the wave file I just inputted. So I can now, of course, play with all the parameters because it's the synth, right? So I can do what I want. Okay, so now let's say I want, I don't know, some other synth, like this one. Whoa. Okay, so you get the idea, something that moves a lot with lots of, I don't know, crunch. Bam! It changed into the new space. And yeah, I'm gonna stop it because it's annoying. Okay, so now what I can do is, yeah, what I said earlier is that I have this space. And this space is actually the audio space, which means the one I trained to have audio similarity, but I can organize it depending on features, for instance, aggressive or something. And the thing is, if I listen to my different presets, yeah, I know why, sorry. I have to, thank you. Okay, so basically I have several different dimensions, and when I listen, for instance, I start, okay. Here my presets, these are all presets from my synth, but they are organized in terms of perception. So if I go, for instance, here, I want to show you also the parameters can move a lot, but it's the same audio. So you see all the parameters change, but I still have the same timbre. I don't know how we say timbre in English. I always say timbre. Timbre. Thank you. Timbre. And if I go down, for instance, it's going to be the opposite. Ooh. You see, it's organized based on the perception, but still you have access to your presets, so you can move across space and find, oh, I like this one, I'm going to find a little bit different preset to start with. So it's super easy to go fast with interacting with synths. Then I can, of course, select a specific, and this is kind of the, yeah, I have one which is actually, this is where you see that I prepared a little bit. And so basically now I'm going to show you my pressure is building now. So basically I hope everything works. So now I'm going to show you the same thing I showed you earlier, is that, you know, I can have my hand moving across space and I can control the synth in a very simple manner. So let's say I have a simple melody and I'm going to show you, so I want to show you my hand and the diva at the same time. So basically, I can go to different parts of the space and have. So I think, yeah, I miss it. I just, I forgot to do something. That's why it was crunchy. Okay, sorry. So basically, if I start from this, then I can move across space, and I have more crunchy things around here. Then I have more high-pitched around here, so you can actually play in real time, and you can see, if you look at the parameters of the synth, everything is moving, because it's moving with an audio perception similarity, and not based on the parameters similarity. So I can actually play this thing, I can add some jazz. Because there is 16 dimensions, so I can play like really softer, I can play higher pitched, or I can go crunchy like this, and I'm actually moving across all the space of the audio of the synth, right? And one last thing, I don't know if I have time, I don't really, right? I don't know, did someone look at time? No? Nobody? Okay. Thank you. So basically, one last thing I can do is a path inside the space was just to show it. I don't remember how I did it. Shade. I don't remember. how do I draw path? How it's going to sound? Yeah, let's say this is a path. And normally I can just kind of loop. I didn't prepare this part, so maybe I'm going to fail miserably. This is going to be nicer. This is a real demo now. So basically, it should start a path. Iteration of path. No, it's the opposite. 16. So now I'm asking the model to make this automation inside the space, so I don't have to move my hands like a crazy person again. Yeah, so this was a messy path. I have to, this is where I can say, this was a demo. Nice. Okay, so I think I'm done with this synth, and we can finish and move to someone less crazy. So, I'm going to end my presentation by just introducing very quickly what you're going to see next. So basically first we're going to have the incredible Antoine you love it when I put adjectives. Sorry. PhD Antoine Caillon, which is working in a team, and is going to show you lightweight real-time interactive plugins and how they can be used in composition. So what I showed you was actually also CPU-based, but most of the other models, they don't work in simple computers yet. We have to use GPUs and large stuff. But the two next presentations are going to show you the future in terms of, I love it, the future in terms of interaction, and then we're going to have the amazing Ninon Devy showing us how we could even go further, like reducing these models. And we worked together with Martin Ninon, and we actually developed this, and it started working 4 days ago. So we're going to see, no, 1 week, I don't know. So it's a very recent thing. We are super excited. It's the NeuroRock. So in terms of future works and openings, I'm going to show you just the little problems we have and we think are very important to address. So the key problem in all this is that most amazing results are obtained with things that have billions of parameters. So it's extremely demanding in energy and memory. So we have the great Constance Douce working on the problematic of green AI and how we can reduce the cost of machine learning. This extends, of course, to the problems of real-time interaction and control that you're going to see with Antoine and Ninon, and also the problem of musical improvisation, with which we work. So we kind of removed some of the works because we had not enough time. So globally, the question is how can we attain true co-creative states with AI? So I love this sentence by William Blake, which is, man's desires are limited by his perceptions. No one can desire what he has not perceived yet. So this is the part where I go into philosophical space. So basically, when we think about objects like AI, and we think they are so complex, actually complexity is just a lack of dimension. You can think about the idea I showed you with a piece of paper. Imagine what's going on when you drop a cube inside this piece of paper. So basically, if you look just at the piece of paper itself, you're going to see a very complex shape moving and you don't understand it. If you find a way to go to this higher dimensional space, it's actually a very simple interaction going on there. So the problem is that we are actually really bad to deal with high dimensions as well. So the example I like to give is, where do you think is concentrated the mass of an n-dimensional sphere? So basically, if you think about a sphere, a ball. So a ball can be a circle. So if you have a circle, you know that it's actually equally represented. But if you take a ball of 3 dimensions, actually, where is the mass of this thing? And the mass of this thing, if you think about n dimensions, the more you have dimensions, the more all the mass is actually concentrated on the surface. So in the end, in ND, 99% of the mass of a sphere is actually just the above layer of the sphere, which is kind of something we can't really wrap our hand around, right? So I think we can escape our own doors of perception through what we are trying to do, artistic collaboration, which spark new scientific ideas, and we usually do most models for specific interest. And this is actually, I think, core of what we are trying to do here. So thank you for your questions, if you have any, by the time Antoine can set up, maybe. Thank you. Cool.
I have a quick question.
Yeah.
So this plugin, the Able Light device where you're showing where you control synth.
Yeah.
Did you try if you take a preset sound from the synth,
Yeah.
the audio waveform, inject it in your device, do you get them exactly the same parameters?
Yeah, that's actually how we evaluate. If you want, I can send you all the scientific paper. It's lots of math, but actually the way we compare, because we tried many different ways to do this interaction. So the way we compare is actually taking the sound of the synth, but sounds that the model never saw. So we actually give some sounds of the synth to the model, it trains, and then to know which one is working the best, we take other sounds that the model never saw, we drop them, and then it can recreate almost perfectly. I think when you take sound from the same synth, it works almost perfect. Then when you take anything outside, it's sometimes yes, sometimes no. And Diva is a little bit too simple. But then the problem is things like Massive or Serum, for instance, they have wavetables. And then wavetables makes, I think, in my head, that they have very weird shapes because you have a wavetable which defines the entire shape of your space. So if you change the wavetable, you're kind of changing completely the space. So I don't know how to solve this yet, but yeah, thank you.
And is that right now trained just on Diva, or can you just drop in another plugin and
yeah, I would love to just drop a plugin and it works. Yeah, that's the future of the future. Yeah, actually I have a PhD student I co-supervise in Tokyo, and he's working with FM8. And so right now it can work with any continuous parameters synth, you know, like additive FM. So basically we need 8 hours to generate a data set and then 12 hours to train. So maybe in one day you can have a new plugin. But it's not plug and play yet, you know, you can't drop a plugin. This was actually long nights of no sleep to get this working. So right now, sorry, it's working for Diva. But yeah, of course, in the future we would like to have like more plugins and more possibilities. Cool. Okay, thank you very much. So we're going to switch.
So hi everyone, my name is Antoine Caillon. I'm currently a PhD student in the Acids team. And today I'm going to talk to you about interactions with AI and how AI can be integrated inside the creative workflow. So in the past few years, there has been a lot of work in deep generative modeling applied to audio synthesis, and more specifically, audio representation learning. That's not good. Yes, okay. So mostly representation learning that you've seen earlier. So representation learning can be seen as a very high quality analysis synthesis pipeline where you can at the same time find the representation of your input signal and then synthesize from this representation. So really it aims at discovering like a hidden structure under the data set you have and can actually be seen. Oh no, that's for later. And it can actually cover a wide range of applications such as style or timbre transfer, unconditional generation if you sample randomly from the latent space, or interpolation and latent exploration if you have an encoder mechanism. So one interesting representation learning model is the variational autoencoder that you've seen just earlier. And it's basically composed of two submodels, which is an encoder and a decoder. And this kind of I'm going to make some poses, that's nice. Okay, so this encoder-decoder structure can really be seen as a data-driven compression technique, but instead of relying on perceptual metrics, such as the MP3 codec, we learn a representation of the data so that we use the compactness of the representation as a way to compress the data. For example, with faces, regular compression technique will try to compress the amount of information that is present between pixels, whereas here we're going to try to find high-level attributes about faces, such as the age of the person, if it's a male or a female, the hair color. And those very high-level features is what is going to give us control on the generation. And one very interesting thing about such compression models is that the more we compress the representation, the more the reconstructions are going to get biased by the data set it's been trained on. So basically, if you have a very low ratio, very low compression ratio, the overall model is going to act as an identity mapping. So it's going to take an input, either image or signal, and just learn to give it back without any meaningful information inside the latent representation. Whereas if you have a very compressed latent space, you're going to get like less faithful reconstructions, but the latent space itself is going to be far more interesting to explore and to manipulate. Examples with faces. So this is from Alexander Schubert's work. If you take a human face and you feed it into an autoencoder, it's going to learn to reconstruct it the best it can, and as you can see, there are lots of artifacts, but it's not like regular data artifacts. It's artifacts that comes from its understanding of what a face looks like, and I guess it's way more interesting than regular JPEG artifact that's kind of not beautiful at all. Okay, in the team, we mainly use representation learning for audio purposes. And when you compare like the advances in image generation and audio generation, we are not at the same stage. There is a lot of work on very high quality image generation, but for audio it's a bit more complex. Because for images, the complexity of the data is quite well structured around very critical points, whereas for audio, well, it kind of spans thousands of samples per second if you're sampled at a very high sampling rate, 24, 48 kilohertz or even 96 kilohertz. You're going to have a model that is able to model those very large very large dependencies. If you want to have a model that is able to capture the dependencies between events that are maybe 2-3 seconds away from each other, it's going to require a lot of memory to train it, and it's going to take a lot of time for synthesis. One of the first model addressing this problem is WaveNet, which is a model that came out in 2016, and which is quite amazing in terms of unconditional generation. It's quite the same results as sample RNN with the Frankenstein stuff you heard before. The only major problem is that it takes about 10 minutes of render time per second of synthesized audio, which is kind of overwhelming. That's nice. I'm going to try to remove the lip motion. You never know. So WaveNet is great, but it's way too long. It takes ages to train and to synthesize. And an even worse and great model is Jukebox, which is a representation learning model that gives amazing results, really truly inspiring audio synthesis, but it's even more than 1 hour render time per second of synthesized audio. So that's depressing. And while powerful, those methods are still to be considered experimental, so there is absolutely no way to use it for an extensive creative use or in any user-friendly audio interface. You can't really interact with it since you have to wait for hours before you hear your actual reconstructions, so you just have to trust your model that is going to give you great results, and the trial and error cycle is going to take ages to perform. And of course, there is absolutely no way to include them in existing workflow in any DAW, synthesizer, or modular. That's out of the question. So what now? We have amazing techniques, amazing models, but it takes ages, and you have to have very powerful machines and a lot of time to create. Fortunately, there has been a lot of work toward creating models that are quite lightweight. That's the case of the differentiable digital signal processing, the DDSP model that you've heard before with the signal style transfer. Well, as you've seen, it's quite a regular like synthesis algorithm with controls learned by a neural network. It uses a previously extracted pitch and loudness to produce another signal. So it can really be used for a lot of tasks such as timbre transfer or MIDI to parameters to audio, which is currently worked on during an internship here at IRCAM by Georges. And the only problem with the DSP is that it assumes that your input audio is strictly monophonic. You can't have two notes at the same time. It has to be either a very simple violin with only one string played at once, or a saxophone, a trumpet. But as soon as you have even two notes at the same time, the pitch extraction algorithm will fail, hence the model will fail too. But if your data set like fits this requirement, it can be very great actually. And the only problem is that the DSP was only available as a command line tool. So you have your folder of WAV files, and you can simply ask with command line commands for the DSP to transform them. So what we did to ease the use of this model is to create the very first real-time external for the DSP. So we built this in C++, and it's basically usable on every OS in real time using a pure data external. So I'm going to show you the teaser we released for the advertisement of our external right now. The model used for this teaser has been trained on 30 minutes of solo saxophone. I think it was like a bebop album, and is used to perform timbre transfer between a simple frequency modulation synthesizer and the target saxophone. So that's great, that works pretty well. The DSP is cool, but what if we want to deal with more complex signals? And this is where we propose the WaveI model that we built from the ground up. This is, again, a variational autoencoder that is trained to model and to represent mel-scale spectrograms. So basically, it's a spectral representation of the waveform that is mapped on a perceptual scale to kind of fit how human hear sounds. And since it's using like regular spectrograms, it can model pretty much every sound existing, from polyphonic music to environmental sounds to noisy inputs, voice, extended play techniques. And so the variational autoencoder outputs spectrograms, which are basically images of sound, and we use a fully parallel waveform synthesis model to transform those images into sound so that you can hear it. This synthesis model is quite recent, and since it's fully parallel, it's very fast, making the overall encoder-decoder model 20 times real-time, meaning that for 20 seconds of signal, you have to wait for 1 second, which is quite cool, given the previous required waiting time. And furthermore, it has a very high compression ratio, which lies between 512 and 1024 times the original waveform dimensionality. And if you recall, when you have a very high compression ratio, you have a very expressive latent space, so that's why it's pretty interesting. So I'm going to make you hear how it actually sounds like. It's only sound, so it doesn't matter. So if you take an input signal, which is this one, we're going to use a model that has been trained on human screams and try to reconstruct this input cat. And same thing with a model trained on weird violence. So as you can see, we keep kind of the same semantic content as the original input. We have the same overall loudness shape, even a bit of pitch somewhere, but the overall timbre is completely changed. The screams model only outputs screams, and so does the violin model. So I think it's kind of cool to have a model that you can control its output by giving it previously synthesized audio and keeping the semantic content of your input, but changing its overall sounding timbre. And yeah. So originally I had created this model as a regular command line interface tool, but I did the same as we did for DDSP. I created a C++ implementation of it that can actually be used as a regular audio effect and implemented in any VST plugin or reactive programming externals such as MaximSP or Pure Data. And for the example, we use actually Pure Data. We provide an already built external for Pure Data that showcases the main attributes of this model. Originally, I was supposed to show you this quick video demonstration, but since I'm running out of time, I'm going to switch to the live demonstration. That was kind of helpful. So, as for the examples, this model can perform real-time timbre transfer. So I have my voice normally inside this microphone. Yeah, okay. So now everything is going to be rendered in real time. So basically, if I enable the model, you're going to hear reconstructions of my voice using the scream model. Sorry. So basically, if you want to kind of control the sound outputted by the model, you can try to imitate pretty much everything with your voice. If you want to go to high pitch versions of the scream, you can. It still screams, but since it's also a real-time application, you can build any type of interactors on this model. So for example, here I have a very simple feedback loop. So everything that is produced by the decoder here is going to be fed back to the encoder using a very simple like bandpass filter that is defined by its frequency and quality factor. So by controlling the amount of feedback and kind of the resonance frequency and quality factor, we can shape the output of the model by simply modifying the filter parameters. And in any kind of regular audio effect, feeding back its output to its input would result in a very weird Larsen and very not pleasing sound. But since it's AI, everything's going to be different now. So I'm going to slowly increase the feedback of the model. So here it's in a pseudo-periodic phase where it's like trying to make a rhythm out of its output. And if we modify the frequency of the filter by increasing it, it's gonna make the pitch higher. So yeah, that's kind of fun, and
Can you add your voice back into it in real time? Or do that?
yeah.
Changes the.
You mean reapplying feedback to it?
Yeah, would it modify that like loop?
Yeah. It's gonna be weird, but let's try it. Hey. Yeah, it kind of increases the bias that is already applied. Originally, I was supposed to make you hear.
Should just be a stand-up comedy.
Yeah, really. Well, I shouldn't. I'm not supposed to laugh, but yeah. And you want to laugh? That's pretty. Yeah. So yeah. Reconstructing a laugh is
joke. Wow. Hello. Not nice.
So anyway, this model has been trained on screams. It's about 2 or 3 hours of screams. Don't ask where it comes from. But basically, you can train this model on pretty much everything. We've trained it on violins, on voice. And yeah, it's pretty quick to train, and everything is done in real time. Just as a disclaimer, I'm using this computer since it has an NVIDIA GPU on it. So we can't really use this on CPU. It's almost real time in CPU. It's taking like 110% of the available, which is not good. I mean, yeah. But if you have even a weak GPU, it's seamless. So if you have any questions, or if you want to try to scream, or you're welcome. And anyway, thank you for your listening.
Quand je passe, il faut que j'appuie. C'est ça.
C'est ça.
Ok. Ah, c'est pas le bon truc. Ah. No. Yes. Okay. All right. Hello. Well, thank you for coming. My name is Ninon. I'm first PhD. I'm studying AI applied to music. And yeah. I'm really happy and really proud to present you this project, which is Norak. Also, I'm scared because, yeah, you're a lot in this room. Yeah. So we are a team of 3 people. Myself with Philippe Essling, that you know, he's here. And Martin Ver, who's not here, but yeah, anyway. And yeah, we worked a lot on this project, which began like 1 month ago. So it's a very young project, and we had our first sound, 1 week ago, something like this. So we worked really hard to show you something cool, something interesting. I hope you will like it. So this is the first AA-based instrument, and plus it fits in your rack. Great. Okay, so I'm just gonna give you a brief introduction just for you to have a context of the impediment and the obstacles, but you actually had a glimpse with Philippe and Antoine. Then I will just talk to you about the design process, how we proceed to build this little pearl. Then hopefully the hardware, but yeah, as you can see, it's just a prototype, so maybe it won't just collapse. Maybe not, hopefully not. But yeah, it's not stable yet. And then finally the perspectives, what we want to do more, the improvement, the future. So yeah, introduction, general problematics and AI boundaries. So first, our goals. Like in our team of 3 people, we are passionate about synth and music, of course. So the goal is to design the next generation. What is the next generation of instruments? Maybe we could actually use AI directly to have like a new tool for musicians, maybe, hopefully. Enhancements of creativity and a new approach to think and compose music, as you understood with the presentation of Philippe. But there are a lot of obstacles, and the biggest one is the model's complexity, because if you want to have like a precise and like beautiful sound, then your model has to be very big and very complex. And as you understood, if it's super complex, it doesn't work anymore. Oh shit, well, sorry. If it's super complex, then you cannot have a real-time generation, or you have to use specific hardware like GPU. So this is the most difficult part for us to design an instrument which is actually standalone, real-time, with AI in it. It's a lot of conditions. But we have some solution. So solution 1 is compression of models. We take this very big model and we try to just cut and crop it and keep the essence of it. And there is this lottery ticket hypothesis, which is kind of new, who's saying that you have this very big neural network, and inside it you have sparse, little small networks which are still efficient. Well, of course, it's not as simple as it is, but this is the key point, the key idea. The second solution is to have an adequate hardware, and there is this little one from NVIDIA Jetson Nano. I don't know if you heard of it. It's like kind of small. You have it on the desk like this, and you have GPU and CPU in it. So this is the 2 solutions. So, in our dream, we want to build this beautiful AI instrument. It must be musical, which is actually hard with AI, as you've heard. But it has to be musical, generate interesting sound, of course. Controllable, this is very important. What do we want to control? How do we want to play with it? So the interface must be handy and easy, because of course we want musicians can play with it, and not only the nerdish scientific who worked on it. It must be real time, and this is hard, as you know, and standalone, because well, we prefer to play without any computer and in a Eurorack, of course, so standalone. Well, okay, that was for the context. Now, the design process. So actually, the workflow is on 3 steps. First, the model selection. What do we want to hear? There is an infinite possibility about the generation. So the third question for us was, okay, what do we want to generate? What is interesting to generate? It has to be musical and expressive. Then the compression, how much can we compress our model? It's about finding the right balance between compress the model but not losing way too much accuracy, like it has to be lightweight, but okay to hear, kind of. And then embedding, so how do we want to control it? So creative interaction and manipulation of the new sound. For the model selection, I don't know what's happening with my presentation. It was supposed to arrive step by step. That's okay. So yeah, the model selection. We choose impact. Why did we choose impact? Well, first because I love impact. And Philip does love impact. But also because with regular synthesis, I don't know if you try to synthesize impact. And by impact, I'm meaning impact, not kick. Because some of my colleagues, they told me, yeah, you're working on kick synthesis. This is really simple. No, it's not. So I just want to be clear with you. This is an impact. And this is hard to synthesize. I mean, with Eurorack. So yeah, I tried, I failed. So at the end, I finished with some sample. If I want to use impact, I finished with some sample. So we said, okay, let's create a little model with AI that can make impact. So how does the model operate? Philip took care of the crafting of the model, but it's basically, you have 7 descriptors that I put here. So loudness, percussivity, noisiness, tone-like sound, richness, brightness, pitch. So you give some graphs to the model, and it can synthesize the sound. So you give it this, and it generates this, which is not bad. Then the interface. So, as I told you, we began this project only 1 month before, so we had no time to really compress. We choose to use this Jetson Nano. So it's a bit more, like, it takes a little bit more space, but that's all right. And then we had to think about a nice interface that could fit with all the modules in your Eurorack. So this is the second prototype. It looks good, I think, but it's our baby, but yeah, it looks good. So then it fits, it's very small, you can see it after with the camera. So you have our screen, you can display the menu and navigate through options, button to select and click, rotary, and audio out. And the more interesting parts, 2 gates here, if you want to play with it. So the first gate triggers the generation, and the second gate triggers the interpolation. So interpolation is like you take 2 impacts and you try to merge them. You take a little bit of this feature from this impact and a bit of this feature, and you try to mix them. So yeah, 2 gates, one to trigger simply, the other one to trigger the interpolation, and the rest of the button are for CV. With the CV, we choose, but this is of course the first prototype, and we have so many stuff to do. So we choose for one CV to be responsible of the amount of interpolation, and the 3 other CVs are for the amount of features. I can't remember what are the features we choose actually.
Yeah, it's actually flatness, centered, flatness, brightness, and
well, we tried with all the features and we choose 3, and we can't remember because it was probably like 2 days ago and we didn't really sleep in between. So yeah, so this is the Eurorack. So I'm gonna try live demonstration and pray Ganesh it will work. Okay, oh yeah. So this is the size in my case. As you can see, it's very small. And I'm going to play with this one because this one is working and this one is not working yet, but soon it will work. So it's not the same disposition, but here you have the gate, here gate, and the others are CV. As you can see, we have the screen, which is displaying the logo of our group. Okay, let's try it. Okay, so it's driven by a gate, so if I move the frequency, yeah, it's working! All right. A bit more difficult. CVs. Yeah, it's merging those two sounds. All right. So, yeah. Merci. We tried a lot of stuff, and I can't show you everything. So I just made, I just gathered all the beautiful impacts we had and made kind of a track just for you to listen what is it capable of, because I think the impacts are beautiful. All right. So just the last words about the perspectives. So about the prototype, of course, there is so many stuff still to do. We would like to have final CVs, final gates control, develop nice-looking menu because this one is quite harsh. Maybe include VAE so that you can actually travel inside the latent space and generate your impact traveling inside this latent space. About new module, of course we would like to compress the model to get rid of this Jetson Nano and just have this little module to run on CPU. Why not trying another sound generation? Because impact is fun, but maybe something else. The interface, well, we are a big fan of EuroRAC, so we choose EuroRAC, but it's actually possible to have like more box, maybe include movement, the movement of the musician or a dancer, I don't know. And for the discussion, well, the best for us is to have actually your opinion, your wishes. Maybe you have some ideas because you are a musician. And if you want to try it, of course, we will be glad to give one to you and you try it and you give us some feedback. Well, thank you.
Okay, so you're still up for 15 minutes about spatial audio, or you're getting tired? So very many thanks to Philip and his group. I'm very, very happy that they trained the machines on your music and they spent a lot of time to make all these demonstrations work. As you've seen, it's brand new research on the EuroRAC and whatever. I'm more presenting also outcomes of new research, but something we do since 25 years now. So it's well settled. It's all about spatial audio. So what I see, what we see now, because when they talk about training the machines and they don't have enough CPU and they need GPUs and whatever, and it's not yet working on a single computer, that's the problems I know when I started with spatial audio. I don't know if you have ever been working on a next step machine. I think most of you are too young. But with the 8-channel card of IRCAM, so this was back in 1995 something. So we shared the same problems. We needed too much CPU to run high channel counts and whatever. So 8 channels being crazy, and then 98 was my first 16-channel dome. And nowadays we end up with what we call high-density loudspeaker arrays. And that's something I work a lot, so which doesn't mean that I don't use less than hundreds of speakers, but using hundreds of speakers is a lot of fun because you can do things which you can't do before. And nowadays it's easy to set up spatial audio systems. It's easy because on the one hand we have 20 years of research, algorithms are ready, they are stable, they can be used in real time. We have the software plugins, still struggling with 60 channels, internal bus structures in all the digital audio workstations. So when you want to work with hundreds of channels, you need to outsource your plugins. And so there's the question, of course, we ask ourselves, how many channels are enough? And does it make sense to use hundreds of channels? And yes and no. So I'm very pragmatic. I have some ideas on what sound should sound in space, and then I search the model which works for me. It might be a 6-channel environment, it might be 700 of speakers. It's not the same aim. So when I talk about high-density loudspeaker arrays, so that's what we call the simple mobile array. It's 128 speakers. You hook it up with a Dante interface, so you run some Ethernet cables and that's it. Self-powered loudspeakers. Now you may say, okay, for electronic music it might not be enough sound power. Yes and no, because if you use very many small speakers, they can output also a lot of sound power. Of course, then if you go to bass frequencies, that's why we have subwoofers, or even we extend it with line arrays or whatever, then you might want to have additional sounds. But that's what's normally when I work with people coming from electronic music, they say, I need sound power, I want to use an ambisonic dome with 16 speakers, but I've seen you use tiny speakers. yeah, but we use tiny speakers because the space we play in, if I use an DMB E12, it's a powerful speaker which is enough for Cité de la Musique in Paris or whatever. But if I want to feed a spatial audio system for 20,000 people, then I replace the speaker by a line array. It's exactly the same thing we do with stereo or mono or whatever. So we are very interested in those such arrays. So we have, unfortunately, we cannot visit our concert hall. It's a 350 speaker setup we have there. So it's one going around the audience, bars of loudspeakers for wave feed synthesis in a dome with at all 100 speakers for higher audio ambisonics or whatever system you would like to apply. Unfortunately, when we built the system back in 2011, so we inaugurated the system in 2012, and during installation we found some asbestos. So we closed the space in 2014. Now it will reopen in 2022, and then there will be some renovation works at Centre Pompidou, so we risk to close the space again in 2023. So it's not always COVID, which is challenging, but anyway. So during the break, because we didn't have our concert hall, you may know Johannes Goebbel, one of the co-founders of ZKM in Karlsruhe. So he built up in upstate New York, it's MPEC, it's the Experimental Media Performance Arts Center, which is an amazing space in the middle of nowhere. But they have a wonderful concert hall, they have studios which are well equipped, and he said, okay, you cannot do your research, so you may want to come over and you say what you would like to do, and I try to get the funding. So that's wonderful, that's Disneyland. So we build up, so that's the first prototype of a wave feed synthesis system. So the final version of this system is about 700 loudspeakers, which can be run from 4 computers in parallel, which is fair for 700 speakers, I think, and which can be complemented by a dome of 64 or more speakers, so to have 3D audio, like all around with height audio, and what we call wave feed synthesis, and I would like to come back to wave feed synthesis in a second. So for us it's important because we do, actually for me it's very interesting to see all those guys working in artificial intelligence now, because one of the breakthrough of our software, which is called SPAT, was that it was one of the first perceptual models on spatial audio, because back in 1985 they got sick of composers asking how to control this parameter in acoustics, what's the impact and whatever, so they did research on the impact, so the mapping of perception to the control of the device. So it's simple in spatial audio, so they didn't train neural networks, they trained the neural networks of the researchers to find some equations that work, which actually work quite well. So recently we've been also working with spherical loudspeaker arrays to project sound into a hall, which is very interesting because you can, especially in industry halls, where you can work with reflections of the walls. So it's an interesting model. However, so what's interesting about wave feed synthesis? I don't know if you have ever experienced wave feed synthesis. Yes and no. So the easy part is, so we recreate the wave field. So wherever you are in a room, sitting, because normally with stereo you have the problem, the closer you the speaker, you hear the sound coming from the speaker. With wave feed synthesis, we recreate the sound field which travels in space. So no matter where you are in the space, you hear the sound field or the sound source at the correct position. So especially for installation or when people are not seated and can walk around or whatever, you have a very stable spatial image. But it comes for a certain price, and the certain price is hundreds of speakers. But there is another effect, and that's something which I very much appreciate about wave feed synthesis. It's something which is called in front of the array of focused source. A focused source is, so we trick physics, because normally we cannot recreate the sound source in the space, mathematically speaking, in the space where we recreate the sound field. So there is no mathematical solution for this. And treating this, it's very tricky. But what we do is just, we solve the same equations and we play them in the different directions. So normally, if you look here, the sound travels from the closest speaker to the farthest away speaker. So we use the same filter sets and start with the farthest away speaker, and we move the sound to the closest speaker. And what happens is the sound source which was before behind the array swaps in front of the array. And when I say swapping, and that's the huge difference, I can create in front of you, for example, where this little stereo microphone is, a sound source when the array is here on the back of the stage, which is physically there. You can stick your hand into the sound, you can use a microphone array and measure the sound. It's there. You can even explode soap bubbles on a glass of water because the energy is there. The only thing is you don't have the vibrating body in front of you because all the vibration is coming from the traveling wavelets. The body is outsourced. The body is behind the array. It's the speaker array. And that's very interesting, especially when you would like to address the audience. So you have a sound installation, then you move some sound into the audience. There are many constraints because we trick physics, but it's a very interesting part. So as you can see here, the sound source was before behind the array. So now I start playing it from this direction. So from the farthest away speaker to the closest speaker. And so all the, oops, okay, we have to wait again. Oh, come on. All the little wavelets superimpose in one point and create this sound source. So you could create a virtual band group playing here, and the singer is just in front of you, and then you can even render the directivity. So you see from this point on, the sound source is recreated physically, and it's there. And I think with this technology, we come into something which we call sound sculpturing. It's in terms of doing art with line arrays, a very interesting thing. And we had a very nice installation by Daniel Chanteau and Daniele Ghisi. I just plug in the stereo. Je prends le 2. So the installation was in 104 where you will perform, and the installation was called The Body Talks Alone. So Mon corps parle tout seul. So it was very interesting because they created a wall of fog. They projected a big mouth on the fog. It was in a dark room. I'll show the picture here. So you cannot see the line array, which is way behind this object here, which becomes a real object because it's a video projection on this fog cloud. So it becomes a very lively object. And then we created a focused sound source inside the mouth. So when you come closer, you not only see the object, you can also hear the object. And it's in the same physical spot. So it becomes a physical sculpture without seeing any speakers or what else. So I think it's a very, very interesting installation, which very nicely shows how waveforms. We don't hear it here, but it's just that you see how it looked like.
J'ai mal ici, non là, à la tête, au bras, à la main, j'ai mal au doigt, celui-là, l'index, le majeur, j'ai mal au ventre, j'ai mal au genou, ça doit être une tendinite, j'ai mal partout.
Nous avons beaucoup travaillé le support vidéo.
So
Nous projetons sur
he just explains that they projected on the sound, on the fog cloud.
rideau de brume. C'est comme si cette bouche qui est suspendue dans l'espace, flottant dans le vide.
So it's like being alone in the space.
J'ai jamais senti aussi bien, c'est presque inquiétant. Je vais pouvoir courir toute la journée.
L'ensemble de l'installation est plongé dans la pénombre et je pense que le
Which is
calme,
the,
ça
I think you got it
amène,
how it looks like. So that's very interesting. So there's on the one hand wish how to move sound in space. The problem with wave field synthesis is you are not allowed to be in between the sound source, the focused sound source, and the array, because otherwise you just will have phasing artifacts. So with Michael Charel, in his piece in 2010, we've been asking this question because he wanted to have sound surrounding the audience, inside the audience, directly projected in there. We cannot just move a sound source around because you will always be in some kind of phasing. But what we did back then was to use granular synthesis. Because when you have voice, it was vocal snippets, and the little snippet appears next to your ear, you feel immersed into this point cloud, but you don't hear the trajectories, so you don't hear the phasing artifacts. And so we created with him a huge fog of sound snippets around the audience with a frontal array, and it worked quite well. So it doesn't make sense, a lot of sense to show it in here because I don't have a wave field synthesis array.
And the same here, there's a piece by Jonathan Harvey, it's called Rizzicare una melodia. So that the trombone player here triggers himself, so he loops himself with a foot pedal. And then a lot of electronics is going on, from pitch shifting and creating 4 alter egos of the trombone player on stage, and he interacts with his alter egos. And so what we did, beside the trombone player, there are 4 virtual sound sources, even with directivity, that they sound natural in the room. And he interacts with them live. So I show you a short excerpt. So the first is a simple Rizzicare, is a canon structure. So he starts playing, loops himself, and then the other ones create the canon. Of course, it does make a lot of sense without having now the beauty of virtual sound sources on stage. But we performed this at AMPEC because we did a workshop on spatial audio, and Penny was playing in New York, and he was coming to AMPEC and just performed a piece. And then a young choreographer and art director, Andrew Schneider, was currently working at AMPEC. He was in residency to work on a piece where he explores a lot stroboscopic effects on stage. Maybe I show you a quick example of the way he's working. Just give me a second. Yeah. Oop. Does it work? Sorry for the loud sound.
Doctor says you have 24 hours to live. That's the good news.
I'm still here. And I'm still totally not sure why you aren't talking to me. Talking with me.
No, wait.
I'm right here.
Go, 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 go! Get out! Get out! Go, 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 go! Get out of here! No, no.
So it's very impressive because it really tricks your vision, what's going on stage. And he wanted to work on this piece, on a new piece, which is called After. So you hear an actor, you see an actor on stage, he speaks, you have a stroboscopic light, some seconds or milliseconds, and then in the next moment, the next phrase comes from a look-alike actor on another position on the stage, and goes back and forth and back and forth. And then a third person appears somewhere, either with the same voice, with a different voice, and then there comes synthesis and everything, and it really, you get crazy when you look at this. You know the installations by Turrell, they have the stroboscopic effects, and then he just shuts it off, and you see a white wall, and you have the beautiful colors because your brain is overloaded. And that's what they do with people. And so what we did is we co-localized. We even tricked it not only with one condition, but also with audio. So you see somebody, you hear somebody from the same spot. Then you see the same person a millisecond later from another spot, and you hear him or her there. Then you see him here, but you hear him there. Then you hear him there, but you see, and it goes on like you have the total overkill. And then, you know, I don't know if you know the installations by Turrell, then he reduces very often to 4% of light. And then your brain needs to adapt, and then you see silhouettes and shadows. And what they wanted to do then, with Bobby McElvor, which is sound designer of Andrew Schneider, they wanted to then move the sound from the actor through the heads of the people in the audience. And that's this really crazy moment, because you see, first you're completely overloaded, so people start to scream, to cry, to whatever, because their system is close to the breakdown. And then you get to silence, then you see the silhouettes on stage, and then the sound of the silhouette moves through your head, and you have the impression that this ghost comes through your head. And that's the moment where during the first rehearsals we had to introduce some system of little light sticks, because some people couldn't stand it anymore, and that we can search them in the dark space because it's very aggressive. But the problem in terms of audio was, as I've been saying, I cannot move a sound through the audience without having this phasing artifact. So what we did is, we've been hanging wave-field synthesis arrays from the ceiling, projecting the sound from the ceiling down to the audience, and then moving it straight on the line. So we had 6 line arrays from the ceiling, and then we could move the sounds through the heads. And it really comes, you hear the voice, it goes in your head. It sounds like a mono sound in your head, and then it disappears to the back. And this was the stage setup then, and it worked amazingly well. It needs some time of setup. But for me, it was this moment where I could really feel the sound, or this multimodal sculpture. So that's a very interesting part to work with wave-field synthesis, because to project sound very close to the audience is something which is very, very interesting. And of course, we are not only working with wave-field synthesis, we work with all the different technologies in research, like ambisonics, because you can record it, you can have nice 3D recordings, you can transform sound on the recordings. There's a nice piece by Natasha Barrett where she uses a balloon, puts a 3D microphone inside the balloon, uses whiteboard markers, which she moves around the balloon, so you get very natural trajectories, and then she applies sound transform on the sound she recorded in 3D. And it's a very impressive piece. Unfortunately, it doesn't make sense to show it here because it needs a dome of speakers, but that's a very interesting thing. I skipped, because we started late, we are running late, I skipped maybe just some words on David Munaki. So he was recording in rainforests since 15 years now, 3D recordings. On the one hand, it's research. He wanted to understand, or better understand, the communication in between species. So what you can see here, it's a spectrum of different animals communicating at the same time. So they share communication channels as we do. So you have high-pitched communication, lower-pitched communication, whatever. What's a little bit depressing, not a little bit, when you compare his recordings from 15 years ago to nowadays, you can see how you get dark zones in the spectrum which you had before, because we lost many species. And we've been working a lot with him on the encoding of what he was recording. And what's impressive is when you play back his recordings on a 3D dome of speakers, how dense it is, how very many different colors you have in there and whatever. So he's starting also to compose with all this material and so on. So we use this material very often to work on encoding, decoding, because it's not a musical content. And on the other hand, it's very rich. So it's very rich to to have all the spectrum and whatever. So recently we've been working a lot with Natasha Barrett and the open-ended group. So they did a very nice installation. There's no sound. Let me see. Which is called Pockets of Space. So it's a 3D video and audio installation. So you have a stereoscopic screen. You have that's our nearby mobile dome of 64 speakers, which is set up for a different performance, or has been set up for different performances. Now it works. And the open-ended group, they do very nice visual renderings, very fine structured. Then you have the dome playing back the sounds. Oh, that's all, okay. And a little bit inspired by the work, we have since 2020 something which we called musique fiction. So we invite different composers just to work on this dome of 64 speakers. So you may know the dome, not Klang Dome, your dome. No, not the Kubus, the mobile one you did.
Oh, the Hexadome.
The Hexadome, yeah. So we've been collaborating a lot together, also working, they partly use our software as well. And here we have our kind of mobile version. So that's a version for stage setup with 64 speakers. And there will be soon a standalone version with, I can't remember, also about 50 speakers or something for traveling. And we invite composers artists, not only composers, to create little sound works on immersive audio, which is, in my opinion, very interesting work. However, so just to go on with this. So one of the problems is that we cannot project sound, or it's difficult to project sound into the audience. So there was, I think 5 years ago, a project which was called COSIMA, Collaborative Situated Media. So, or as Norbert Schnell would have said, COSIMA equals people plus smartphones plus web standard times anywhere at any time and all together. So this was his equation for what it should be. So we just use cell phones to, so you come to the concert or whatever, you connect to a server and we project sounds on your cell phones. And since we have very many cell phones, so in the concerts we equip the cell phones with little speakers. And so you have a little handheld device and you can create and move sounds through the audience by the cell phone. So for example here, that's a demo, it's just some cell phones on position on the table. So you get a little interface, and with this interface you can move the sounds through the cell phones, and that also visually you understand where it comes from. Since we cannot set it up here, you see the lights of the phones. And then you can swap control. And as a follow-up project, they've been working together with DJ Chloe. And so we started to develop devices for her that while she's on stage playing and performing, that she can project sound. She can take one sound from her turntables or whatever and define it with a button. That's my sound I want to throw into the audience. And since she'll most often not have time to move the sounds around with the finger, David Poiriquino started to develop some rules. She could apply presets like pouncing off walls, virtual walls, and so on. And actually, although it's tiny speakers, it's very impressive when you're very much immersed by these little loudspeakers around you and surrounding you, which makes quite a lot of sense. Of course, you don't get a lot of sound power. And the performance is limited to, let's say, 20 minutes, because when the cell phones run out of battery. That's another drawback. But, you know, you need constraints to do some artwork. So that's also something about, I think what's interesting, we're getting more and more interested in getting away from dome-like structures, line arrays, to more non-standard setups of loudspeakers. And for example here, an installation I did with Mark Fell, you know him, it was in the Sage in northern England. So we've been playing on this wall. I don't know if you know the Sage. It's on a hill, it's a concert hall, it's like a bubble. And you have a very nice view over the city, and we've been invited, it's the entrance hall, and we've been invited to use this huge window to play with the window. So we installed a kind of speaker array, which you can see here, the speakers. It's been about 60 speakers. It's about 100 meter long, and I can't remember the height. I think I have another picture. Maybe, I don't know. So the idea was that people could capture sounds with their cell phones. So it was about daily sounds they like. Then they could upload them on a server. Then we used orchestration. So each sound was decomposed in a maximum of 50 virtual sound sources. They've been played then by musicians because all the automatic orchestration didn't work properly. So we've been working with an orchestrator. And then what's nice is you can, if you play them back from a single spot, like the first sound you hear, it's a windmill. Then it sounds like the windmill, and then you can spread out the little sound snippets over the space, and then you can hear into not the partials of the sound, which you would do by spectral analysis, but the components in terms of music. And this was very nice, or very well done, and it moved around, and you can do all this in real time. So that's the windmill, so you can hear the strings, wind on strings. So that's the structure here. And then we could decompose the sound in real time and it moved around in space. And that's how it looked like in the stage. So it was very, very nice view, but in terms of sound spatialization, it's not so easy to play a wall of speakers. We have a lot of experience playing with domes of speakers, with circles of speakers, with linear arrays of speakers to do spatial audio, but with non-standard setups like a grid of speakers on the ground and whatever, it needs a lot of technology and know-how to handle this. And this brings me to the know-how you need. So we've been developing now since, I think 20 years, 25 years, our software which is called SPAT, which started as MaxMSP externals and more became proper software. And which is quite interesting here, what you see, it's called panoramics, because our sound engineers, they've been getting sick of making MaxMSP patches for concerts and whatever, and we've been working together just saying, okay, what's the sound engineer's view on spatial audio? So they just wanted to have like a mixing desk for spatial audio, which makes a lot of sense. The only problem is when you deal with a high number or a high channel count, we couldn't do a plugin because we are limited to 16 channels, and that's normally not enough. Reaper is now on 64 channels, so if you work with Reaper, and we very much hope that Ableton and other software companies open up to multi-channel audio. It seems for Ableton at least it works better now. In Ableton you can trick with the MaxMSP devices for Ableton, because you send in between the devices and just get rid of the internal pass structure. So I just show you very quickly what panoramics looks like. So what you have here, that would be a typical panoramics channel. So I get, for example, rate of the mono bus, and I would just say, hey, okay, I have, well, let's say two mono inputs. I have an eigen mic, so a 3D ambisonics microphone input. Just need some time to create. I would like to route all this to a multi-channel bus, which then could be ambisonics, vector-based amplitude panning, binaural, stereo, whatever you name it. There should be nearby everything in there which you would like to work with. Let's say we work with 4th order ambisonics and 25 channels, and that's it. So that's the setup. You just feed in your audio files, you route to the buses, so it's like a mixing desk, and then you route. Then you set up your speakers, and you have your up and running spatial audio system, which you can then interface with OSC. So all the parameters can be remotely controlled by the digital audio workstation, which makes a lot of sense. And so we have, so normally the way we work, we have one computer doing the digital audio workstation, so the arrangement, the cutting, the whatever. Then we have little plugins which allow for OSC communication. Then with 2 RME cards or with Ethernet, you can easily send hundreds of channels in between 2 computers. And then you remotely control the software, and that's it. Of course, there's one drawback. We cannot bounce offline. So we are back to when I was trained as a sound engineer. We are back to real-time bouncing, which is really annoying. So we very much wait for having more support from companies like Pro Tools, Avid, Ableton, and others to fully integrate spatial audio, at least with 64 channels. Hey, we're in the 21st century. 64 channels should be fine. I'm not asking for way more, but 64 should be fine. And then, of course, for me it's interesting because, in my opinion, now we have all the tools, we have sufficient enough processing power, and what's missing is artwork which really explores spatial audio. So, of course, we have a lot in mixed music. It comes a lot from mixed music. But for example, in electronic music, there's way less, and I think we can do way more. And since we have the tools, it's easier to explore. Of course, then there's the question, you don't want to draw trajectories in your Ableton or whatever, so that the sound moves in a spiral. So, for example, we integrated SPAT into Open Music, which is a kind of meta programming languages, so we can say, you can put some rules to create trajectories, and then you can scale them and whatever, and it's nice because you get a kind of MIDI control track which you stick to your sound and then you screech it or whatever. And then of course, for those who work more in pro audio, they don't want to have Max MSP running or use other tools. So we work with, for example here, a company which is called Flux. So to do a nice plug out, it's not a plug-in, it's also standalone software running, but with fancy graphical interface and whatever. I prefer the less fancy panoramics because I want to have my CPU power for sound and not for vision, but of course it's very nice to use. And recently we've been working also with Amadeus, so they've been building a standalone server which feeds 120 input and output channels, so it runs a kind of our software in there, and it's all for pro audio and spatial audio, so which makes a lot of sense. So actually I wanted to give some demonstrations here, but I couldn't downsize my sound files, which are normally rendered to 64 channel domes and whatever. I didn't have enough time to put it to the 6 channel version here. But anyway, I think what's interesting is, from my point of view, that we have the technology, we have the software, we have the speakers, and it's, as I showed in my very first slide, go back. So for example, that's a 50 channel dome we've built up for a concert of Olga Neuwirth in the Elbphilharmonie. We had 1 day for setup. We had the show and built out the same day after the show, and that's it. So we had 2 days more or less in the hall, and it worked quite well. It was tough, but it worked quite well. And actually, when people complain when they talk about spatial audio, you need so many speakers and whatever. Take a roadshow, I don't know, use Metallica or use whatever. I use a single van and they come with 15 trucks. So of course they have more people. But we are little players. So I think what would be very interesting, so we have of course here a lot of experience with mixed music and less with electronic music, but I think there's a lot of potential what you can do with spatial audio in electronic music, and it's not yet that explored. And also personally it would be very interesting, so I did a lot of work with Mark Fell, but he has his own particular installation style, you know him, also with other people, but I think we could do way more in this direction. Okay, this was just a very quick, I keep it short because we are already half an hour late. I just wanted to show you that the tools are here, the technology is here, the interest is here, and I would be very happy when the things spread a little bit more out to electronic music, other than only mixed music, what we mainly do here. And we've seen with the fiction, the musique fiction, it's very interesting what appears from younger composers who really want to get into this. Okay, so this was just a very, very quick overview without sound examples, which is my fault, because I was trying to do some mappings and whatever, but I was running out of time. So, okay, I think that's now the time to open discussions, and we just wanted to give you an impression that deep learning, artificial intelligence even fit in nowadays into the Eurorack. At least it's experimental, but it fits in there. And also with spatial audio, it's a little bit the same, that we can do a lot of things which we couldn't imagine before, and it's easy to set up. And now I think it would be nice to stick the heads together to get some ideas, your creativity with some backup of technology to create some maybe common projects. So that's it. Yes. That's a good point. That's a good point.
We are already super late, huh?
Yeah.
Because of Frank.
Est-ce que je peux débrancher?
Thank you for the presentations. Thank you. Thank you. Thank you for the presentation. Sounds like there's a little